So shall we start? Okay. Hello, everyone. I'm Jang Lee, and it's my great pleasure to introduce our visionary speaker today, Professor Roger Jang. Professor Jang received his PhD from EECS department at UC Berkeley, where he studied fuzzy logic and the neural network with Professor Nabi Zadeh. And I think most of you may know that Professor Zadeh is the father of fuzzy logic. And Dr. Jang is now a professor in the Computer Science and Information Engineering Department of National Taiwan University, or NTU. He has also served as the IT director for NTU Hospital and the director for FinTech Center at NTU. And I think his most famous work is that he has generated many data sets for corpora for various applications, such as speech, image, music, medical, and the wafer map dataset. And his dataset of wafer map has been used in many ITC papers in recent years. And this year, we have 2 paper sessions dedicated to wafer map analysis and classification. And most of those papers refer to his wafer map dataset. In fact, I just checked Google Scholar today. His work has been cited over 62,000 times. It's really a large number. He is currently also serving as CTO of E.Sun Financial Holding Company at Taipei. And today he will give us a talk on machine learning and corpus design for EDA and beyond. So let's welcome Professor Roger Jang.
Okay. Thank you very much for the introduction. I'm Roger Jang from Computer Science and Information Engineering Department of National Taiwan University. It's a great honor of me to be able to give a visionary speech at ITC. As you may know, I'm not a test guy, but I do have ample experience in machine learning for over 30 years. So today I'm going to discuss machine learning and the corpus design for EDA and beyond. So I'm going to cover 2 machine learning examples in EDA, including wafer failure map analysis and the side channel attack via server map. Then I will share my tips in preparing corpora for machine learning. Okay, wafer failure map analysis. I'm going to talk about this and with focus on detection and prediction. So the goal is pretty simple. We want to detect and classify wafer failure map, and hopefully with high accuracy and efficiency. So this research is based on a 3-year project with TSMC back in 2011. And we have 2 references about our research. The first is a journal paper published by my student back in 2015. And the second one is a master thesis of my student. But actually, the second paper is an extension of the first paper, although, chronically, they appear to be reversed. So here we can see some typical failure map for small die wafer. You can see this is localized. We have a sector here, a center here, an edge here, a ring, a scratch, and a complex here. And hold on, let me change it to this icon, which is more visible. So here, as you can see here, we use different color to indicate different defective type of dies on the wafer. And if there is a specific failure map, that means there must be something wrong in the recipe, or there must be a specific type of malfunctioning in the machine. So we want to be able to identify the failure type as soon as possible and locate the root cause and fix it. And you know, at the end of the day, we want to optimize the overall yields. And usually this is done by human to check out the wafer map again and again. And now we want to automate the process. So during this project, we have also constructed a data set. It consists of around 8,000 K maps, and about 21% of them are labeled by experts in TSMC. And all the wafers are classified into 9 different classes, including 8 types of failure map, which is called pattern wafer because it has some failure pattern, and also 1 type of normal map or non-pattern wafer. As you can see here, all the 9, a typical wafer of these 9 classes are shown here. And the first 8 are pattern wafer, and the last one is non-pattern wafer. So as far as we know, this is the first large-scale real-world wafer map dataset. So in order to do machine learning, we need to partition the dataset into training and the test. We use about 31% of them for training and 69% of them for testing. In particular, all the wafers for testing is carefully picked by domain expert at TSMC, and this is a major effort. It involves a lot of manpower. And here we can see some bar chart of the composition of the training and the test set. Of course, to do machine learning, we need to extract feature. So the feature is actually the deciding factor for a successful classifier. Our features are composed of a Radon transform, geometric features, and other miscellaneous features. But since we don't have too much time, I'll walk through the slides quickly. So the first one is Radon transform. It's based on projection. For instance, if you have a column here, it's actually a projection along different direction, and to get the intensity, and the intensity will be one single column on this map. And here is a very innovative animation. We are doing the projection on the horizontal side. As the pattern is rotating, you can see the result after the projection. So after Radon transform, we are going to get a response matrix like this. So this is a 9 typical wafer map, and this is the corresponding matrix after Radon transform. And then we can take the row mean as a feature or row standard deviation. So you may wonder why we always take row-based feature, because we want to make the feature rotation invariant, and also to make the feature scale invariant. We always need to divide the feature by the area of the wafer or the perimeter of the wafer. So here we have some other feature. This is a geometry-based feature. This is a region attribute. For this wafer map, we can do some region labeling, and it keeps the largest area as the region for our analysis. So here there are a bunch of equation here, but I won't go into detail. If you are interested in this formula, you can take a look at our journal paper. And similarly, we can extract some statistical attribute, like the standard deviation of all regions, so on and so forth. Then we can also find the line and the curve attribute. For instance, here we can use half transform to find a line on this wafer map, or we can use polynomial fitting to find a fitting parabola here, and trying to compute some attribute as features for classification. And because the features are most important for classification, so I encourage my student to, try to devise as many different features as possible. Here we have a different group of features. This is a 15 binary pattern of 2x2. We have 4 of this kind, 6 of this kind, 4 of this kind, and 1 of this kind. So totally we have 15 of them. Then for each wafer, we can compute how many of them in each wafer to get a 15-dimension feature. And another one is the count of corners. You can compute this by the Harris corner detector. So as you can see here, if we have a near full pattern, then the number of corners will be smaller. On the other hand, we have this kind of sporadic pattern, then the number of corners will be higher. So in order to perform some analysis, we use 2 different tests for our research. The first test is based on the original whole data set. So it includes both small dice and the big die wafer. And let's take a look here. We have it's blocked by the text bar. But here, actually, you can see this is a small die wafer, and this is a big die wafer. Because for small dice wafer, the resolution is higher, so it's easier for us to extract reliable features. On the other hand, for the big dice wafer, the resolution is lower, so the extracted feature is are not as reliable as the previous one. But remember, for the test 2, we want to do our analysis on a subset of the data set with the dice count from 300 to 500. So this is a big dice wafer. Why do we need to focus on the prediction of the big dice wafer? It's simply because for each die on this wafer, it has a higher value. So, but the performance of prediction actually is not as good as small dice wafer. So we want to improve the prediction of big dice wafer in order to increase the productivity and the value of the whole wafer. So here for both tests, we have a 2-stage classification. For the first stage, we want to identify the failure map. We want to detect the failure map. We want to separate the normal wafer from the failure map wafer. And at the second stage, we want to do this failure map prediction. So for the first one is a binary classification. Especially, we need to pay attention to data imbalance problem. For the second one is a common N-1 class classification, or we'll refer it to its performance as a remove non-accuracy because the non-pattern wafer was removed. Of course, we can combine 2 stages to get a N-class overall accuracy, but it's not good enough because by combining them together, we won't be able to see the breakdown statistics of each stage. And both stage are we use support vector machine for both stage. So here we want to do a binary classification to detect the pattern wafer from the non-pattern wafer. We use the feature of geometry-based and the radon-based. And of course, we can do some noise reduction here. Here we are using a median filter to do noise reduction. For the donut type, after noise reduction, the donut shape will be even more visible. But on the other hand, for this H-ring type, after noise reduction, we won't be able to see the vivid structure of H-ring. So we don't know if we want to use this noise reduction technique or not. So one way you can do is simply have a 2 set of features and concat them together to get a feature set of 1/16 dimension. So here is the plot. The green line here is with noise reduction, and the red line here is without noise reduction. And if we combine them together, we can get a better DET curve here. So by combine two sets of vector, we can get a better performance. And this is the final result of 9-class classification. As you can see here, the best accuracy is achieved by this near full class. It's about 98%, because it's pretty easy to identify this type of failure map. And the most inaccurate class is the localized, which can achieve only about 70%. So because the localized pattern will have a region appear at a different location, and maybe their shapes are also very different. And here we have some other confusing map, which is hard to classify. For instance, these two types, we have a center and a swirl. And it looks almost the same. And here we have a localized and a donut. Again, it's pretty similar. So that's why this kind of wafer map classification problem, sometimes it's not well defined. So so even for human, they have a different opinion. So for our test 2, we want to do the classification with wafers of dice count from 3 to 500. So we have 5 class here. And then here we want to do ablation study of the feature used for our experiment. Here we have a 306 dimension. That means this is a complete feature set. So we are going to use this complete feature set, and we are going to remove these 2x2 binary patterns to get a partial feature set with dimension 291. So as you can see here, the removed non-accuracy is reduced from 91% to 90.7%. So that indicates the importance of 2x2 binary patterns. Next, we are doing the same. Here we have a complete feature set. Then we remove the feature group of corner count. And actually the dimension here is only reduced by 1. And the accuracy is reduced from 91% to 88.8%. Remember, there is only one feature missing, and the decrease of accuracy is quite significant. This indicates the importance of this count of corners as a feature for this classification. Then we can do sequential forward selection. This is a way to select the important features one by one. And after the sequential forward selection, the dimension is reduced from 306 to 163. And the accuracy was boosted from 91% to 92.1. And next, we can try the feature transform using PCA and LDA. By using PCA, we can reduce the dimension from 306 to 132. And then we can apply LDA after PCA. It can reduce the dimension from 132 to 114. People may wonder, why don't we use LDA directly? But it's impossible, because if you use LDA directly, you are going to run into some problem of rank deficiency. So this shows the result. After using PCA and LDA, the dimension was reduced to 114. But the accuracy only boosted a little bit, only increased by 0.1%. So here it shows a summary table. The full set, we are going to get 91%. But if we use any partial set, the accuracy will be lower. But if we do, feature selection, then the accuracy will be boosted to 92.1. If we do PCA and LDA, it can only boost the accuracy by only 0.1%. So the best one we can obtain is this full set and perform a feature selection. So how about the error type? Here we have so many different error types, but since we don't have too much time, I will skip this part. Especially, if you can see this ground truth for this one, This is actually a new failure type, but the ground truth is centered and our prediction is localized. So you can see there are some new pattern not been labeled correctly by the by TSMC people. So the benefit of TSMC, our system has been put to TSMC, and only less than 10% of all joint development program with university have been put to production. So our performance in the project actually is pretty good. And from reliable source within TSMC, we can save up to 100 million USD per year for TSMC. And actually the system is still evolving, because whenever you have a new recipe, you have a new machine, then you are going to have a new failure pattern. So people are still using, to do manual inspection to some degree to identify a new pattern. Once there's a new pattern, then we need to do labeling and perform modeling again. So this is kind of the necessary step in the so-called MLOps, machine learning operation. So the take-away message, feature engineering is necessary so we can optimize our feature, but don't overdo it, because if you do it again and again, you are going to run into the risk of indirect training on the test set. And here we use handcrafted crafted features to make the system explainable to some extent. Like you use the count of corners, you can see which pattern has a more count of corner, which pattern has less. So, and we want to make sure it's rotation invariant, scale invariant, and dice count invariant. So people will ask, why don't you use end-to-end CNN or DNN? The problem is, if you want to make to achieve those this above invariance, then you need to do data augmentation. Then you are going to get 10 times, 100 times number of data. So you're going to carry out massive training. This is not so desirable, especially it's not friendly to our environment, and it's also less explainable. Okay, so the second small topic is about side channel attack with a thermal map. So I'm going to cover machine learning based side channel attack for POI selection in thermal emission. So our goal is to decrypt AES-128 key using thermal map, and hopefully we can locate leakage tiles on a chip. So the assumption is we can send a lot of plain text to the chip and obtain the encrypted text as output. And then we can do reverse engineering to find the key of AES-128. But actually, I'm not an expert on information security, so this part I'm not so sure. But actually, this is a joint project with ANSYS. But I can get the data from them, so I can process the data to get the performance and get the result. For reverse engineering part, that's their job. So AES-128 involved the use of 4x4 matrix. As you can see here, we have a 16 byte. So we are going to build 16 model. Each model represents the output of a byte, and the byte can have 256 classes. So the input is a thermal map. The output is the value of a byte between 0 and 255. So the full chip thermal image represent the average temperature during an encryption process using a given plain text. It's the data is based on ANSYS simulation tool. The size of the thermal map is 201 by 201. So our model will have a 201 by 201 input. So it's a lot of input, and we can collect around 20K images using 17K for training and 3K for test. Here is an example of plain text, and we always use a single key in our experiment. Sometimes we use tile to refer to the pixel in this thermal map, and for a single image, we also use the term trace, which is used in the security community. So when the chip is doing the operation, actually there are only 16 tiles is doing the computation. And this, if we do a zoom in or cross up, we can see the location of this 16 tile. This is called operating POI. So the operating POI represents the most power consumption because its activity is much higher than other tiles or other pixels. So we want to use machine learning to identify these 16 operating POI. So our approach is based on a preprocess in order to sharpen the image and to imitate the power map. And then we use machine learning for classification and use feature selection in order to identify the operating POI. So this is a thermal map like this. But actually, we can get a power map. Power map is more can be used to more precisely describe the activity of each tile or each pixel, but it requires a precise measurement and always hard to come by. So it's easier to get a thermal map. So one thing we can do is trying to convert thermal map into a power map. So as you can see here, the thermal map is actually it's a blurred version of the power map. So we can try different sharpening filter. We have to try this Sobel filter, pre-weight filter, and the Laplacian filter. And it turns out Laplacian filter can get the highest Pearson correlation. So we use the Laplacian filter as the process for process the thermal map. So after the processing, we can find the standard deviation or the variance of each tile. And we can, select the top 200 tiles for further analysis. Because, whenever there's a higher variation, that indicates, there are more activity going on for that tile. And so all 16 operating POI can be included when n is equal to 200. For the evaluation metric, we can use cross entropy loss, we can use ranking, we can use RTD. When I say ranking, that means we want to rank the output of each model. And if we have enough input to the model, we can compute the log probability. And as we have more and more data or more and more trace coming in, then we can accumulate all the log probability, and the right number or the right class will be moving up to the top. Usually we use RTD or required trace to disclose. It's the minimum number of trace required, for correctly to stay at rank 0 in a stable state. When the RTD is less, that means it's easier to crack the byte. Here we are using CNN for prediction, but actually the prediction is okay, but we can get the heat map. But heat map, as you can see here, the heat map can cover the 16 operating POI here, but there is no precise indication which one is more important for the classification. So the next step, we are going to perform line up selection. We can line up all the 200 tiles and then select them one by one. For instance, in round 1, we use tile 1. Round 2, we use tile 1 and 2. Round 3, we use tile 1, 2, and 3. So eventually, we can reduce the number of tiles or number of POI from 200 to 137 for byte 0. So this is a plot for the blue line here is for the RTD, and then the orange line here is for the loss. So actually, we can do better by using another selection. We can perform sequential forward selection by selecting 8 POI or 8 tiles from 137. And actually, the operating POI for byte 0 is number 49, which will be selected as the 8th POI in this sequential forward selection. So the summary is here. By using machine learning, we can find the keys for AES-128, and more importantly, we can find the leakage tile by perform a sequence of feature processing. Here we can reduce, from 200 to 137 by sequential forward selection, by line-up method, and from 137 to 8 by sequential forward selection. But actually, we can reduce further by using exhaustive search. I think we can reduce it into a smaller number. But this will be our future work. Okay, the last thing I want to talk about is 5 minutes. Okay, tips in corpus preparation and also for high citation paper. As you can see, why you care about corpus preparation? The bigger reason is we want to advance humans' research frontier. But for me, my reason is much smaller. I only want to increase the citation of my paper. So corpus sources, there are different sources for corpus. You can do self-made. For instance, if you want to collect some speech corpus, you can have a student in the lab to do some recording, or you can create a platform like those game with a purpose, so people will come to your platform to leave their data. It's not so easy. So the most variable corpus is from industry or from company, because this is a real world corpus. When I was collaborating with TSMC, I told them, you guys should convince your boss to release the dataset, because if you don't release the dataset, my student's paper won't get accepted easily. If the paper don't get accepted easily, my student won't be able to get his degree. So if he knows he won't be able to get a degree by doing this project, he won't be able to put all his effort into the project, and then you get nothing at all. So eventually they bought in and release the dataset. So actually for the wafer failure map paper, the methodology is no big deal. But I think my biggest achievement is convince TSMC to release the dataset. So the basic tip for dataset, you need a README file with a version number and the change log. As also, you need to provide the information how to cite the corpus and cite the first paper. Presumably, this is your paper, the first paper using the corpus. For other advanced tips, you need to provide code tools and code for corpus processing. This is sort of outsourcing, so people will keep on working on your project and provide some feedback. You need to list subsequent papers for people easier to do citation. And also you need to construct a dedicated website for the corpus. So here is the this is the page of our corpus. We have been collecting corpus for over 20 years. So here is a lot of different corpus on speech, music, and wafer map and images. So here, since eventually, for me, I want to get a citation of my paper. So here I want to share 3 tips. First, you need to release everything. You need to release your code and the corpus and make it always available on the internet. So, and your paper's focus should be method, and the method should be of general interest to the general public. So this can let people to try your methods on their publication, on their application, and then they'll cite your paper. And then you should try not to perfect your paper. This is the most important. You should leave some room for improvement from others. It's like you have constructed a path, leading to a magnificent waterfall, but you don't want to, convert the path into a super highway. you should let other people do it, and other people will, cite your original paper or your original work. So here I do have some some paper that meet all the criteria. Here is one of my first journal paper. It was published in 1993, which is a while back, and the citation is almost 20K. Actually, as I say, the methodology is not so much of a big deal, but it meets all the 3 tips here, so it gets a lot of citation. So I think this concludes my talk today. Hopefully, after my sharing of the tips, everyone can get high citation papers. Thank you very much.
Okay, thank you, Roger. It's a great talk and a very practical one. You actually teach us how to get data set from TSMC and also how to increase the citation number.
Okay.
Because I think we have run out of time.
Oh, sorry about that.
I will still take 2 questions from the audience. Okay.
Okay.
The first one is from Edward Seymour. Is your prediction specific to a minimum feature size?
My prediction for the side channel attack, I do try to reduce the feature size. Because if the dimension of feature is smaller, then the computation will be faster. But for the wafer map prediction, I want to optimize the performance. So there's some trade-off,
Oh, okay. And another question is that the semiconductor process continue to improve over time, and the new shapes either show up or may no longer be valid. So how often do you need to train your model, or how to enable self-adaptation to keep the model consistently at the decent accuracy?
Wow, this is a big question. It's very important, but it's very hard to achieve. For instance, if you want to identify new pattern, you need to perform some kind of anomaly detection. And after you have the anomaly, you need to actually, it should be determined by human. So this is an outlier, or this is a new pattern which will be, will appears again and again. Then if you want to make your system adaptive, that means, which I assume the adaptive means there's no one to supervise the machine. But this is very risky because we always have someone to step in to take a look at the machine, take a look at the output to see what's going on. So we can do adaptive only to a certain degree. Yeah, I don't think it's impossible to do everything automatically.
Okay, thank you. Since we have run out of time,
Sorry.
I have to close the section now. So
okay.
Thank you again. Okay.
Thank you.
Yeah. Okay, so I would like to remind the audience we have a break for maybe 20 minutes now. So please visit the exhibition lodge or go to the public area, and so you can have some social activity there. Okay, thank you for your attention.